And today we have John Fidel came here. So Fidel basically is doing his PhD with mm, Kavan Modi at Monash University, and he has been recently working on quantum error correction and has a very nice paper recently on detrimental non-Markovian errors for surface code memory. So today we are pleased to have him here. Fidel, maybe you could start the screen sharing and
Yep.
present. Yeah.
Just let me know if this works properly. Can you see this?
Yeah, I can see this.
Okay. Okay. I guess I'll start now. Okay. My name is John Fidel Cam, but you can call me Fidel. Today I'm going to be presenting a recent study we did. There's a paper associated with it called Detrimental Non-Markovian Errors for Surface Code Memory. Okay, and there's the archive link if you want to open up the paper on your own. Okay, let's start. We'll start with motivation and overview. And to do that, I will open up with this meme. Uh, One of the central theorems of quantum error correction is the threshold theorem, which states that below some physical error rate, you can achieve fault tolerance, meaning you can suppress your logical error rate to arbitrarily low levels in order to perform arbitrarily long computations. One caveat with this, though, is that a lot of the original sort of derivations of the threshold theorem assumed identically distributed, uncorrelated noise. And what happens if you start putting correlations into the noise, you can kind of see a breakdown of the threshold theorem. So to kind of illustrate this, I'm sure everyone has heard of or read the recent Willow paper by Google, quantum error correction below the surface cold threshold. And one of these things, so I got this figure from the appendix, was that about once an hour, there appeared to be a correlated error burst event that would cause a logical error for a high distance repetition code on their superconducting device. So there are actually two logical error modes, and you can look this up on the supplemental material for their paper. One of them was you had a lot of these noisy detectors going off at once, so a lot of these syndrome measurement flips, that you sort of had this sudden burst at once, and the detector error rate, or the rate at which detectors went off, would decay exponentially over time. The other one, that I think was also maybe even more interesting, is that you had this single noisy detector event where you had this one single detector that would experience a very high detection rate for an extended period of time. And the actual detector would change. So it wasn't always the same detector that would go off like this. So kind of thinking about non-Markovianity or temporal correlations in our noise models. How you can kind of think of them is that you have your quantum system, which is going to be a quantum device, which you have access to. How kind of non-Markovianity arises is that your system will be coupled to its environment or bath, sort of represented by the circuit where you have your system and environment evolve over this joint unitary. Non-Markovianity kind of arises from this interaction, but where you only have access to the system. I'm not going to go into too much technical detail here because this is still the motivation, but you can kind of apply this view to a lot of the types of correlated error mechanisms we see in, for example, superconducting quantum devices. For example, for two-level systems, you essentially have these hidden environment qubits that you don't have access to that will couple with your system qubits, or maybe even, for example, leakage errors, where the larger Hilbert space is the higher quantum energy level that are outside your computational basis. So why should we care about non-Markovian errors? For one thing is that these correlated error mechanisms, say if you have your joint system environment unitary, depending on how strong that coupling is, they can increase the overall physical error rate, pushing systems potentially above your physical error threshold. But sort of what we're going to focus on in this study is that the temporal structure, or just the structure of correlated errors themselves, can interact non-trivially with your quantum error correction scheme. We'll sort of get more into this later, but for example, you could have a space-like or a time-like error string that will lead to logical errors depending on, what your experiment is and of a correlation error structure. Okay, so just to give an overview of the study, we're really trying to answer the central question of how does the temporal structure of non-Markovian noise affect surface code performance separate from the overall error rate? And this is kind of the emphasis of this is that, sure, you measure some physical error rate for your system by randomized benchmarking or some method to measure the physical error rate. And that might be below threshold. But I think what we'll kind of see going through this is that the correlations affecting your system can also be important and can actually be really detrimental even though your average physical error rate might appear to be below threshold. So sort of how we do this is that we want to analyze surface code memory performance under different temporally correlated circuit level noise models. We compare this directly to the performance under independent circuit level noise, meaning the marginal error rates, the average physical error rates are the same, but the actual joint probability distribution is very different because it's uncorrelated. And then and that's 2 and 3. We carefully construct a noise model so that the marginal error rate is identical for both correlated and independent scenarios. And what we found is, to summarize, certain temporally correlated error events can significantly degrade surface code performance, in particular, streaky multi-time errors, especially affecting syndrome qubits. Now, kind of how we phrased this study, detrimental non-Markovian errors, is quite pessimistic. And indeed, there are definitely some error structures that are really bad for error rate scaling. But as we'll kind of see, there are also a lot of temporally correlated error models where surface code memory fares pretty well against. So yeah, it's not all doom and gloom, but this is, I think, an important result to go through. So to provide a bit of background first, I'm guessing this because the seminar is specifically QEC related, people are very familiar with the toric code, the surface code, so I'm not going to spend too much time here. But the quantum error correcting code we're primarily working with in this study is the rotated surface code. Your surface code, how do you model noise? One of the main ways to model noise these days is circuit level noise. And basically, in that noise model, all it is you have a perfect application of a quantum gate. So for example, your measurement reset or CNOTs. and that's followed by a error channel. In the diagram here, in this case, these are going to be your bit flip channels, your depolarizing error channels. And one way that people kind of classify errors, so if you read Austin Fowler's Towards Fault-Tolerant Computing paper, is that you can divide them into class 0, class 1, and class 2 errors. Class 0 errors being your errors on your data qubits before your syndrome extraction circuit. Class 1 errors being your measurement errors on your syndrome qubits, and class 2 errors corresponding to the entangling gates throughout the circuit. And another thing I'm not going to go into too much detail is these different classes of errors mapped to different edges in your detector error model. So if you have a class 0 error, that will appear as a space-like error on your syndrome graph. If you have a class 1 error, that'll look like a time-like error. And if you have a class 2 error, if you have a certain class 2 error, that might look like a space-time-like error, alternatively called a hook error. One other result from the literature is how sensitive is the surface code to these different classes of errors. And I took this result from the Austin Fowler paper, where for independent noise, logical error rate is least sensitive to class 1 errors, is more sensitive to class 0 errors, and is most sensitive to class 2 errors. So you can keep this in the back of your head because we will touch on this later on. Okay, so how is it that we're constructing our temporally correlated noise models? The way we did it in the study is, you have your circuit level noise model that we showed in the previous slide. And in essence, what we're doing is we're creating correlations between these different gate level error channels. So again, you start with your gate-based or circuit level noise model. And what we're going to do is introduce temporal correlations across these different noise channels. So essentially what we're doing is we're inserting multi-time poly channels throughout the circuit. We saw before an example of a 2-qubit depolarizing error. This is kind of off of that, but instead of a 2-qubit depolarizing error, it would be, for example, a 2-time depolarizing error. We have a depolarizing error on qubit 1 at time 1, and followed, and then later on at time 2, you have another depolarizing error on the same qubit, and these errors will be correlated. Specifically in the study, we focus on within class inter-round correlations, so correlations that span multiple rounds. So for example, you could have a temporally correlated class 0 error, and that would correspond to your error on your data qubit before your syndrome extraction circuit at round 1, and then another one, for example, at round 2. So that would be a nearest round correlation. We also look at different correlation structures. Mainly in this study, we look at long-range 2-time or long-time pairwise correlated errors, and we also look at multi-time streaky correlated errors. So the spatial kind of analogy of this is that your pairwise error, your long-range pairwise error would be your qubit on this side of the circuit, on this side of your quantum error correcting code might have some correlations with an error on a qubit on a different area of your surface code. Right. Just kind of maybe illustrate that more. Here I have examples of class 0 2-time depolarizing channels and class 0 multi-time depolarizing channels. So for the long-time pairwise case, for each pair of rounds, what we do is we apply a 2-time depolarizing channel to the same data qubit at the location corresponding to the class 0 error. So in which case for class 0, it would be before the syndrome extraction circuit. These errors are jointly applied at rounds I and j with a probability that decays with basically the round separation, the temporal separation. On the other hand, with a multi-time streaky error, what we apply is an n-time depolarizing channel that spans a contiguous window of rounds from I to j. So for example, you could have a streaky error that lasts for 3 rounds, where over these 3 different times, you would experience a correlated 3-time depolarizing channel, where the likelihood of a streak decreases algebraically with its temporal duration. And we say decreases
Hey,
algebraically.
Fidel, sorry.
Yeah.
If I can just clarify something. So like this long time pairwise and multi-time depolarizing channels. So like so you apply like the same Pauli errors like with some probability on like this different time points. Is that what it does, or?
Yeah, good question. Not necessarily the same Pauli. So you know how in a 2-qubit depolarizing channel, you have like a 1 in 15 chance of like x, y, x, z, and so on.
Okay.
In this case, it's like, well, it's n time, but it would be like an equal chance of xxx, xxy, and so on.
Okay.
Yeah.
Okay, sounds good. Thanks.
Cool. Okay. And sorry, where were we? Right. When we say decay algebraically, we mean either polynomially decaying or exponentially decaying. So, for example, the probability of a temporal long-range pairwise errors goes to AQ over I minus j to the power of n, where AQ, here A is the model parameter, Q is your characteristic physical error rate, and then I minus j are just your rounds. Oh, and n is another model parameter here, where, for example, n equals 2, that would mean your correlated error probabilities are decaying quadratically. And conversely for exponential decay. Okay, just some more notes on this. In the case of class 2 correlated errors, we apply 2-qubit 2-time depolarizing channel. So you can kind of think of that as like a 4-qubit depolarizing channel, but it's split over 2 rounds for the pairwise case, or a 2-qubit multi-time depolarizing channel for the streaky case, specifically targeting the same entangling gate between the same 2 qubits across multiple rounds. So it'll in this case, like we kind of model it as your gate becomes faulty for some period of time. Okay, another thing is just how we sort of construct these error models, which is essentially, you can kind of think of it as a hidden Markov model. Is that marginal error rates are not necessarily temporally homogeneous, meaning if you, for example, focus on a single round and you measure the Pauli error channel for that round, it's not necessarily the same as the next round. But what's really important in the study that even though there is this temporal inhomogeneity, that the marginal error rates are matched between the correlated model and the independent model. So they're only different in their joint distribution. Okay, so yeah, this how we achieve that is we have this sort of procedure for mapping the different temporally correlated models to independent models. I'm not going to go over too much detail in this, although feel free to stop me and ask any questions anytime. But I would encourage you to check out Appendix A of our paper for more details on this procedure. But overall, I think it's like quite straightforward. But it helps to reparameterize your error models in a manner that you see on the slide now, because that allows us to utilize useful properties of maximally mixing channels and how the statistics of those channels sort of combine if you have multiple channels that overlap. So for example, you have two 2-qubit depolarizing channels that might overlap on the same qubit. How do those errors add up? Sorry, give me a second. Okay. Yeah, so again, I'm kind of going to overfly over this, but if you want more details, check the Appendix A of the paper. Just to talk about some of the methodology we used for our numerical simulations, we used STIM, which I'm sure many of you have heard of already. It's a high-performance simulator for simulating and analyzing quantum circuits, stabilizer circuits. Sorry. Specifically, though, if you've used STIM before, you probably also might know it's not super straightforward to implement these arbitrarily correlated error channels, in which case you would need to rely on stim.flip simulator, which is sort of like the class for a low-level simulation where you basically do the Monte Carlo sampling of errors on your own rather than letting STIM handling it, where in that case, STIM can really only do limited correlations. For our decoder, we use min-weight perfect matching via the pi matching library. Okay, so let's go over the main results of this paper. In this experiment, what we do is we plot the logical error rate per round versus surface code distance up to distance 15. Where here we have temporal correlations for class 0, class 1, and class 2 errors. So all classes are correlated. Again, reiterating that we focus on intra-class correlation. So class 0 errors are correlated with class 0 errors, but not necessarily with class 1 errors. The probability of correlated error here is quadratically decaying, so n equals 2. And we list some of the model parameters here. I think this might be slightly incorrect. A for class 0 should be, I think, 0.5 here. You can check the paper just to be sure. But yeah, so it's a surface code memory experiment over 2D number of rounds with 10 million samples. What you can see here is that on the top panel of our figure, this is for quadratically decaying long-time pairwise correlations. And what you can see here is that between your correlated and your marginalized independent model, they're actually very similar. So, and you'll see that for our Tower crop distance projection, they're basically the same at 27. And this is for a characteristic physical error rate of 0.1%. Where the narrative changes pretty drastically is for the streaky correlated model. Where here, if you follow the orange trend, which is going to represent your marginalized independent model, that follows that sort of expected exponential suppression of logical error rate with increasing code distance. But it is absolutely not the case, however, for the streaky correlated error model, where instead of observing this expected exponential suppression of logical error rate, what you get instead is this much lower than exponential, probably the power law suppression of logical error rate, which is something you definitely don't want for your fault tolerance scheme, because the whole point of quantum error correction is that by increasing code distance, you can hit these really low logical error rates of 10 to the minus 12 and are necessary in order to consistently run, for example, your Shor's algorithm. Here are some more plots relating to the threshold. So you have your pairwise correlated, pairwise independent, streaky independent, which look like more of your conventional threshold plots. But streaky correlated, it's quite interesting in that you still do see this initial crossing of logical error rates like you would see in your normal threshold plot. But what's really different here is that you can kind of see this bunching up at the lower physical error rates with increasing codistance. So whereas you can kind of see this fanning out for all of the other plots, for the bottom left panel in this figure, you have, sorry, give me a second. Sorry, can everyone hear me?
I can hear you.
Okay.
Yes, same here.
Thanks. Yeah, where you don't see the expected logical error rate scaling under the streaky correlated, as you know, we would show more explicitly in this slide. So there is also like the question of whether you can even call this a true threshold, because you're not getting the associated behavior from like an actual threshold. So, but I think regardless, the result is clearly not good in this case. So what we want to do next is kind of break this down on which error correlations are particularly detrimental for your surface code. So we have the class 0, class 1, and class 2 correlations. What we want to do is kind of break them down according to the different error classes and seeing which classes of errors are kind of are causing this detrimental behavior. And kind of, I think an initial intuition of this we have is that for your surface code, you have your space-like, time-like, and space-time-like errors where if you have temporal correlations, what you would do is that you would kind of stack these edges on top of each other. And the idea was that time-like errors, when you stack time-like errors together, they kind of coalesce into one larger time-like error string, which is going to be really harmful for decoding, because what happens is that you can get the logical errors that don't necessarily span, that not necessarily caused in a single round, but are actually logical errors over time. If that makes sense. So, yeah, just iterating more of what we do here. We want to find out particularly what kind of correlated errors are detrimental. So what we do is restrict correlated errors to a single error class. For example, correlated class 0 errors. We might say that errors, class 0 errors, so errors on data qubits, are correlated, but then we keep independent class 1 and class 2 errors, so your measurement and your entangling gate errors. And then we, same like the previous results, we compare it with the marginalized independent model where all errors are uncorrelated. You can see those results here. So as you can see here, on all the top panels, class 0 pairwise, class 1 pairwise, class 2 pairwise, you see this you see this expected behavior of exponential suppression with increasing codistance. As for specifically why you might see some of the behaviors here, so for example, for class 0 pairwise, it actually looks like the the blue line, which is your correlated noise model, has a steeper gradient than your independent model, meaning it actually might have a slightly lower teraquark projection. We're not really sure why that is. Similarly for the class one is maybe a bit more predictable, a bit more expected, because relating back to how time-like errors might stack up with each other. But really, I think the two plots that get the most attention here are your class one streaky error model and your class two streaky error model. And like what we saw when we had temporal correlations for all classes, class one and class two, we see this strongly slow of an exponential suppression of logical error rate with increasing codistance. If you're wondering why, for example, the orange trend of class two streaky is steeper than class one streaky, it's because, going back to previous literature, your surface code is most sensitive to your class two error rate. And actually, with the class one error, so according to that result, your surface code was least sensitive to class one error. But here we see your class one error. The surface code can be really sensitive to correlations with class one errors. And as a reminder, class one errors are your errors affecting syndrome qubits, your measurement errors, your reset errors, and so on. Yeah, so just bringing up the previous result of least sensitive to class one, more sensitive to class zero, and so on. Okay, another thing we wanted to find out is how do strength of correlations affect your surface code performance? So really trying to quantify how correlations might affect surface code performance. What we do is, so previously we were mainly looking at quadratically decaying correlated error probabilities. In this case, we expanded it to faster than quadratically decaying, so cubically, quartically, and so on. And also, what happens if your correlated error probability decays as some exponential? So as you can kind of see from, for example, the top left panel, cubic, so your quadratic suppression really is just not good and leads to impractically high qubit overheads. Cubically suppression does seem not as catastrophic, but it does result in an appreciably high qubit overhead. But as soon as you reach quartic or higher suppression, then the surface code actually seems quite tolerant of these type of errors. Similarly for exponential, maybe you might have expected this, but like when your correlated error events are decaying exponentially, well, the whole point of the quantum error correcting codes is that logical error is suppressed exponentially with increasing codistance. So it's maybe not too surprising to see this result, but it's good to confirm. And also, you still see appreciable overheads with, for example, a model parameter n equals 2. So you still want it to be sufficiently, you still want the exponent to be sufficiently high for your exponential decaying function. Yeah. Another aspect of this is measuring syndrome correlations. So we have these different temporally correlated error models. What we want to do is, how does that map onto the correlations in your detection events? So your flips in syndrome outcomes. What we here is basically just calculate the correlation matrix, Pij, where I and j are detector coordinates with space and time components. Yeah, this is a pretty common tool, especially with experimentalists. And then we calculate the temporal order correlation matrix, which averages your correlation matrix for all for all S equals S prime. So really just looking at the average temporal correlations between all your detection events. Here you can see really anything class 0, class all of the streaking models, but also class 1 pairwise and class 2 pairwise. You see this, you do see temporal correlations greater than separation of 2 rounds. So also just to reference, if you have an uncorrelated error model with uncorrelated errors on syndrome qubits or class 1 errors, that will result in correlated time-like errors, which are edges in your syndrome graph in the time-like direction, but have only edge 1. And you shouldn't see any correlations, and you shouldn't see any strings longer than that for independent noise. But for our correlated noise models, we do. And kind of just plotting that, I think the sort of why I'm bringing this up is that what we saw previously is that, for example, our class 1 streaky and class 2 streaky correlated error models resulted were some of the most detrimental for surface code error rate scaling. But that isn't necessarily reflected in your detection event correlations. For example, you can still get appreciable detection error rate correlations for round separations greater than 1 for the pairwise model. But as we saw in the pairwise model, a lot of the time they were quite benign. So here in this case, for example, your class 1 streaky error model, the orange triangles, it's sort of middle of the back here. Yeah. Okay, and now sort of talking about limitations and potentially future avenues of research. This really was kind of a pilot study looking at, with kind of the latest tools we have for studying, fault tolerance thresholds. How do temporal correlations fit into that? In the literature, I think there was always sort of this intuition that like temporally correlated errors wouldn't be good for you. But really the whole point of this work is kind of looking at that directly, running these different numerical experiments and quantifying how correlations might affect your surface code memory performance. But with that, some of, I think, potential things to go from here. One of them is that we only looked at memory experiments. If you've read a bit more about, fault-tolerant computation of surface codes, obviously, like you're going to be running a lot more than surface code memory, and one of them is, for example, if you're doing lattice surgery, there's a paper by Craig Kidney a few years ago about surface code stability experiments that kind of represented some elements of your fault-tolerant computation associated with lattice surgery or moving logical qubits around. What would be really interesting is that those stability experiments might actually be more sensitive to time-like error strings than memory experiments, by the nature of how time-like undetectable error strings might be able to like directly flip logical observable itself. Another realm of research is that we are just looking at surface codes here, but there's a lot more out there. And I think one question that's really interesting is that what about these dynamical or strategic codes that you can't really describe as a static quantum error correction code? For example, the first example of this was the Hastings and Haar honeycomb or Floquet code, where instead of the fixed logical observable, you sort of have this aperiodic evolution of your logical observable. And what's interesting is that in the surface code, like an error on a data qubit is space-like, an error on a syndrome qubit is time-like.
query errors is space-time like. For dynamic codes, it's quite a bit more interesting because you can have certain errors on data qubits that have a time-like component. And it might be really interesting to see how different temporally correlated error models sort of relate to these different dynamical or strategic codes. Another one is we did focus on intra-class correlations, but what about inter-class correlations? But also we kind of focused on temporal correlations here. But what about general spatio-temporal correlations? So, you know, what if we combine these temporal correlations with more complicated intercubic correlations or spatial correlations? Another question is, how can we better characterize harmful correlated errors? Yeah, it's like we showed the result with the correlation matrix, but could there be some technique that better diagnoses these harmful types of correlated errors that isn't just, you know, measuring the performance of your code under different error models. And kind of related to this is characterizing non-Markovian noise from synchrotron measurements. You know, there's an area of research in quantum error correction where, like, can we characterize phenomenological or even circuit level polychannels just from synchrotron measurements? But something that hasn't been looked at is in what if these are temporally correlated poly error channels? And something that personally I've been kind of looking at is sort of essentially integrating this with the process tensor framework. So for those of you who might have not heard of it before, you can think of a process tensor as kind of general framework for modeling multi-time quantum processes, capturing temporal correlations and memory effects in open quantum systems. It's a type of quantum cone because, you know, it looks like a cone. But basically, some of the useful tools that the process tensor provides us is that, you know, by treating your different time indices analogously to spatial qubits, you can apply techniques like polytwirling to derive, you know, these temporally correlated poly noise models. But yeah, that's yeah, so that's sort of what we're doing right now, coming off of this previous research. And sort of that potentially might be able to integrate with the strategic code framework, which I'm not going to talk too much about. But yeah. Okay. So just as a summary, the objective was to quantify how the temporal structure in correlated noise models affects your surface code memory performance. Our approach was we applied this mapping between correlated and marginalized independent noise models and compared their performance. So tried to make it as apples to apples as possible. Our main results, we phrased our study quite pessimistically in that, yeah, certain temporally correlated noise models, these quadratically decaying streaky models affecting your syndrome qubits can be really bad. But also, a lot of these temporally correlated error models aren't necessarily catastrophic to your surface code. So kind of the implications of this is marginal error rates alone are insufficient for assessing fault tolerance. You also need to make sure the structure of the correlations in your error model isn't necessarily detrimental to your error correcting scheme. Yeah, and that's it. So thank you for listening to the talk. Yeah, if you're interested in some of the work or potentially have any questions, please don't hesitate to email me. And there again, for convenience, is the paper on archive. Okay.
Cool. Yeah, thanks Fidel for the very interesting talk. So yeah, so Kishore want me to sub in for him. I think he's busy with something. But yeah, yeah, thanks for the very nice talk. So I just have a quick question on your threshold plot. So you mentioned something about like this type 2 error plot that it's not really showing a threshold. So yeah, I'm just trying to understand why it's
Yeah.
not really showing a threshold.
Sorry, so let me bring that up again. Oh, I overshot it. Okay, sorry, this plot, right? The bottom left panel.
Yes.
Yeah. So
Yeah.
I'm
This
not
tricky.
100%. Sorry.
So this tricky one, right? That it's tricky correlated error, like yeah.
Yeah, so I am not 100% sure like what the correct terminology for this, if pseudo threshold might be more accurate than threshold. But I guess the idea is like the whole threshold theorem states that below a certain physical error rate, you get this exponential suppression of in logical error rate. So you get this spanning out if you plot out, this logical error rate versus physical error rate for an independent noise model. That's not the case with streaky correlated error model. You can see like an apparent crossing of, like you would see in any threshold plot. You do see this initial crossing in these different trends with different distances, right? So like for high distances, it is like sorry, for high physical error rates, it is actually worse to increase the codistance, but below some kind of threshold, it is technically better to increase your distance, but you don't get that expected logical error rate scaling. So is it a true threshold? Yeah, I'm not sure.
Yeah, that's interesting. So you're saying like even below threshold. So that's why you said in the conclusion, even though it's kind of like below the threshold, so but you don't have like the same scaling. Okay.
Yeah.
Cool.
I'm just wondering, does it mean that the distance is like plateauing at the error rate? So even let's say you increase the distance to let's say 100, you would still get like the same error.
Yeah.
Would it mean something like
Exactly.
this?
So that's kind of like this plot, right? Where on a logarithmic plot, as you increase the codistance, it kind of, I don't know if it necessarily asymptotes or like just there might be even a case where like in the Bacon short code where your logical error rate can increase after a certain distance. I think the fundamental conclusion though is that this is definitely not good for your quantum computer. Okay.
I
yeah,
want to ask
so-
something else. Maybe. No, please go ahead.
Oh yeah, sorry. So just another quick question. So just going back to like the process tensor and like the picture you have at the start of the talk. So because like okay, so the one that we've been looking at are like this temporally correlated Pauli channels, and I'm just thinking, if we go to like the full process tensor, when where you have like this non-local unitary coupling your system and environment, going from that Pauli temporally correlated Pauli channel to this, does that give you like more general error model? Yeah, I'm just wondering, like,
Generalized in like more than just Pauli or
yeah,
like correlated Pauli.
yeah, like I guess like more general correlation. I mean, okay, so I guess if we go to like this the process tensor picture of modeling the temporal and probably also like probably spatial and spatial temporal correlations. Could that give us, like an error model that is even more detrimental than the one that, we've been looking at?
Yeah, that's a really good question. The most general way to model spatial temporal correlations is, I think, using the process tensor. But I mean, the nice thing about Pauli's is that you can run Monte Carlo simulations of stabilizer circuits. You can input them into STIM to run these surface code memory experiments. But generally, yeah, it's noise is going to have that coherent element.
Right.
Yeah, it is like it is a question. It is a good question of like going from Pauli to general noise, if that's even more detrimental, especially when you consider like non-Markovianity.
Yeah, I'm just thinking if because it seems like in the this even in the streaky error model, like kind of like the temporal correlations are kind of classical.
Yeah.
All right. Whereas like in this case, like you can have like coherently correlated, coherently non-Markovian error. But yeah.
Yeah, you're right. Like these are like classical temporal correlations. They might arise from quantum, your joint quantum system environment evolution, but the question of how in the language of process tensors, you might have temporal entanglement for your process tensor. How might that relate to your error correcting code performance? I don't really know.
Cool.
I want to ask something. I want to ask something. But first, I want to ask about the. Can you go back? You close
sorry.
the PowerPoint again. Yeah. So when you basically implement these correlated errors, right? What kind of model would you assume? Like what physical process could cause us errors? Right?
Yeah, that's
I mean, one thing was like you have some kind of control errors, right? Because let's say whenever you run your quantum computer, right, there's some kind of physical control, right, like with electronics and stuff. And electrons has some kind of errors, right? Like 1/f error model, something like this. Would you think this is the main source, or would you think something else is the bigger source?
Well, I mean, it'll depend exactly on your quantum system, right? Some platforms, for example, superconducting platforms, like your system will readily interact with your environment, but for example, in ion trap, I believe the main problem there is your control operations and how correlations might arise from that. But yeah, like kind of this study is we're not exact. We take this approach where we focus on like the level of correlations that are detrimental and kind of worry about how that relates to your specific physical situation later. So the idea is like you study your specific quantum system, and you do see it might lead to some quadratically decaying streaky correlations. Well, hopefully this study will inform you that you should maybe worry about that. Yeah.
Yes. But the errors you consider is like these XX, like. But do you always take the same Paulis, or you also switch to Paulis?
Yeah, this is just for demonstration. It's in this case we're
considering
considering
like XZ or something, or XY.
Yeah, it
Everything.
is. Yeah, it's like everything. This is just for illustration.
Yeah, sure.
Yeah.
But do you see a difference whether you restrict yourself or not to, let's say, just XX, or you also allow, let's say, XZ? Like because I mean, service code like is a CS code, right? So X and Z can be decoded separately. I assume that's what he did, right? Because you use the perfect weight matching.
Yeah.
But I mean, since you decode separately, you don't take properly correlations account, especially like let's say Y errors are not properly taken account, like you don't catch correlations perfectly. So I wonder whether this will have some effect when you basically have now, because mix this two. So yeah.
Yeah,
check it?
I mean, I haven't tried running just X errors for every error.
Because
What
if
if it
let's say the
was-
X errors don't have issues, right? Let's say if you just use X errors, there's no bad behavior. Maybe this is a issue of the decoder, and by replacing using a decoder which actually probably takes care of correlations, right? Like the machine learning decoder, something that learns, right? And maybe some of these issues go away.
Yeah,
Yeah,
it's
it's
possible. One of
interesting.
the sorry. Go on.
Oh yeah, no, I'm just saying like it will be interesting because like now like your X syndrome and Y Z syndrome could be correlated, right? That's what you mean, Toby.
Yeah, I mean they always correlate because let's say if you have Y error, that also correlates X and
Yeah.
Z errors, right?
Mm.
But if you do perivation, you don't take care of that, obviously, right?
Right.
It still works, but yeah, everything's a bit shaky around now. And for correlate error, I guess everything will get worse. I wonder whether this problem with the threshold comes from that. And maybe if you use a different decoder, maybe some of the error goes away, or use a simplified noise model which doesn't correlate X and Z space.
Yeah, that's a good question. I think there are some like limits to. Well, I mean, for example, this is like an extreme example, but if you just had like a correlated error of X errors, that connect your opposite boundaries, and it doesn't matter what your decoder is, right? Like it's gonna break. But the question of how exactly your decoder can maybe fight against these correlations or compensate for these correlations it's also something that's like ongoing research. I have tried running some like there's Oscar Higgett's BP OSD decoder. I didn't see.
It has the same issues, I think.
Yeah.
Because again, it decodes X and Z separately, so it will not really fix anything.
Yeah. So
I don't think it will help. But there's other advanced version of BPOSD that actually take correlation between X and Z probably in account, like machine learning based BPOSD decoders or hypergraph
like
BPOS decoding.
Yeah, or even just correlated matching. Maybe that's worth trying out. My intuition is you're still going to get similar behavior because. Okay, imagine you replaced a depolarizing channel with a bit flip channel. Yeah, I don't know. I guess that's something worth exploring.
Yeah. I mean, yeah, it would be nice to see. That's what I say. Yeah, regarding the. I forgot what I wanted to say. So it's about the decoding. Oh, yeah, no, I was asking about STIM, right? I mean, because STIM has a certain way how it sets up the detector model, right?
Yeah.
So if I remember correctly, maybe I'm wrong, but I think it generates some kind of linearized model, right? Like basically it generates one instance of the error and then just propagates it through, right? And then builds up like an effective error model, right? Okay, effective detector model. Like I'm asking how STIM basically makes the error model. I didn't use STIM much, but I know like in the paper by Bravi et al., they use such a linearized detector model, right? Because there's way too many errors. So how do you build up some kind of effective error model, a detector model that you can then decode? They basically write down all possible errors that you can have. Then they start propagating to the Clifford circuit, right? And write down basically what kind of logic error this will generate. Then they basically build up some kind of linear model where basically just consider one error at a time. But this model kind of ignores cancellations. So if there's like two errors happening at the same time, sometimes they cancel out. And this is not catched by this linearized detector model. I think STIM uses the same one as Bravi did in IBM uses. So I wonder if this is, I mean, it seems to work obviously, but I wonder once you go to correlate, is this still the best way to do, or maybe there's a better way to somehow build up your detector model that somehow fixes some of the issues. So my question is basically, is there the way that STIM does stuff, how it builds up basically an effective detector model? Maybe that's not the best way to deal with correlate errors.
Yeah.
I mean, just a hunch. I don't understand it either fully, but yeah.
Yeah, no, that's a really great point. So we are using minimum weight perfect matching, which is a graph-based error model.
Sure. But this is the decoding part, right? I'm asking how the detector model is built itself, right? Because STIM builds a detector model, right, to decode in the first place, right?
Yeah.
And this decoder model, like just building up the effective parity check matrix to decode on, already has some approximation built inside. Right?
Yeah.
Because how STIM does stuff, right? The STIM has built some kind of effective model, right, to decode that he then can decode. But the decode, I'm not talking about decode, I'm talking about building the effective model for everything, right? For you that you then decode on. That already is somehow an approximation that's done by STEM.
Okay, so
So
you're
exact to
talking
my
about
knowledge.
you're talking not just about like the edge weights for your decoding graph.
No. I'm talking about the very way how STEM makes models. Not sure if this is exact or there's some approximation behind it.
Yeah,
Because
not
just so
exactly.
because my knowledge, I know that I think it may be a linearized model. Like it doesn't consume cancellations between different errors. So wonder whether or not this.
Okay, as in like if you have a depolarizing channel followed by another depolarizing error channel.
Yes, it would cancel out, right?
But
I think this is not taking account though, like because
this is
in the end,
what...
else the pair checkmate will become very too complicated to decode. So they build up some kind of linear model, like an effective model, and use this to build up the graph. I think it's not. I don't know. Maybe it's not the best way to do stuff. I don't know. I'm just.
If you mean specifically about what happens if you have a depolarizing error channel followed by another one with no gate in between it, that's we kind of cover that here for our mapping correlated to independent noise. There is a way to kind of, if you have a depolarizing error channel followed by another depolarizing error channel, you can effectively combine them into one if you add up the probabilities correctly. That's maybe what you're referring to.
Yeah, but you do this manually, right?
Yes.
I think STIM also does some internal way, right? How to build up error models.
Okay.
So I'm saying like STIM has some kind of way of build up a detector model.
Yeah.
And there's some linearized approximation inside.
Yeah, to be honest,
But my point is it's an approximation in the end. There is some approximation going on. And I'm not sure whether this is the best way to do stuff.
Yeah.
STIM is not exact, that's what my point.
Okay, sure. The way we add up your error probabilities, I'm pretty sure it's not an approximation. It's just exactly like that's how you should combine depolarizing error channels.
But you do this manually, if I understand correctly, right?
Yeah.
But I mean, STIM does stuff, right? Once you put your errors there, STIM does it's magic, right?
Yeah.
And then builds this detector model, right? Detector graph.
Yeah.
I think that may be based on something like a linearization thing, where basically it doesn't consider cancellations properly.
Yeah, I
think that would be interesting to check. Because I know
I will check that.
I'm not an expert on STIM, but I know I use some different package by IBM and Brabi, and it does some linearization there. And I think they followed STIM.
Okay.
So I know it's not exact like they do. So there's some approximation behind.
Yeah.
So I'm interesting. It's not always good to trust software because I know software they do often approximations. So there's approximation there.
Yeah, that's interesting.
That was the point.
I wasn't really aware of this, and I'll look into it further. So, but thanks for pointing it out.
Yeah, because STIM does many things for you, right? But basically, the picture I'm using, everything is like low level, so I can see all these things, and I understand that they're doing some approximations there.
Yeah.
So I just want to let you know this stuff.
Okay.
It's good to consider.
Yeah.
The linearized error model you're talking about is from like this BB code paper, right? Like this.
Yeah. Yes. So that's how I learned everything. But I'm not sure. But I believe STIM does the same because if they claim an online, we copied kind of STIM. So I believe STIM does the same thing. But I don't know.
Interesting.
Because you tell like if you consider all possible correlations, like your model will go crazy, right? So you have to do some approximations.
Yeah, I remember like
you basically simulate each error independently and then build like an effective model, linearized model.
Yeah, they just propagate like each error, like one by one, right? There.
Exactly. Yeah, but of course this is an approximation, right?
Exactly.
I don't know if this will cause some issues once you have more you add correlations, or maybe that's a better way to do this.
I will say it's exactly the same syndrome graph between the correlated model and the independent model because the marginal error rates are the same. So. But yeah. Again, I'm not exactly 100% sure sort of what you're talking about, but I'll look into it.
So you can look in the description in in the IBM paper by Nature. But probably if you look at the Detrimental, they describe how to build up detector models. They talk about this linearization. And I believe STIM does the same.
Sorry, is this like the original Gross Code paper by IBM?
Yeah, exactly.
Yeah, okay, I'll check it out. Yeah. Okay.